Topic which I am going to deliver lecture is on specific gravity in minerals, isomorphism and polymorphism. The module of the lecture includes introduction, specific gravity determinations, steel yard balance, Jolly spring balance, heavy liquids, problem on specific gravity calculation, isomorphism, polymorphism, and the last module is the conclusions. Specific gravity of a substance is the ratio of its mass to the mass of an equal volume of some other substance taken as unity. The specific gravity of a mineral is defined as the ratio of the weight of the mineral to that of an equal volume of water and can be determined conveniently by any standard method. If the weight of the mineral in air is given by W1 and its weight in the water by W2, then W1 minus W2 is the weight of an equal volume of water, and the specific gravity of the mineral is given by the expression specific gravity is equal to W1 divided by W1 minus W2. Specific gravity, or as it is frequently termed relative mass, is entirely independent of the system of weights in which the masses of substance and standard are expressed. Specific gravity of minerals is determined using chemical balance, Walker's steel yard balance, Jolly's spring balance, or specific gravity bottles or liquids. The specific gravity of a mineral forms an important and distinguishing character only when the mineral is either too heavy or too light. In case of minerals of moderate specific gravity, therefore, this character is not of much importance. Moreover, this property of minerals is variable within wide limits, depending upon the nature and amount of the impurities present in them. Among the several physical properties which assists in identification of the minerals, specific gravity plays a very important role in not only identification of the minerals, but also in distinguishing the minerals having the similar other properties. Specific gravity, which is the weight of the substance compared to equal volume of water at 4 degrees centigrade. Specific gravity is directly related to the molecular weight of the elements present and on how densely they are packed. The pure form of a mineral has definite specific gravity, which could vary when a proportion of the constituent elements has been replaced by other elements in solid solution and when inclusions are present. The specific gravity for different end members of the solid solution series and the polymorphic minerals are variable. The polymorphic minerals which possesses the same chemical composition, but different crystal structure show different values of specific gravity. For example, the polymorphic mineral aluminum silicate, that is Al2SiO5, crystallizes as andalusite, sillimanite and kyanite due to the pressure and temperature conditions during their growth. Accordingly, the specific gravity values for andalusite is 3.16, sillimanite is 3.23 and that of kyanite is 3.55 respectively. In the case of solid solution series, the specific gravity varies within the different end members present. Example, in olivine solid solution series, the specific gravity of chrysolite is different from that of phosphorite or fayalite. In such cases, the specific gravity varies depending upon the proportion of the end members. Specific gravity of minerals can be determined accurately by hydrostatic method. For rapid determination, certain heavy liquids can be used. The approximate specific gravity of a proportionately cut gemstones can be determined by using certain gauges. Determination of the specific gravity by using the hydrostatic method is based on Archimedes' discovery that a substance immersed in water replaces equal amount of water. Distilled water is preferred to ordinary tap water because of two reasons. Number 1, the specific gravity of pure water at 4 degree centigrade is equivalent to 1, and number 2, it is free from air bubbles. A simple but accurate mechanical balance is used for this purpose. To start with, the specimen is weighed in air and then its weight is taken by immersing it in water. Difference between these two readings provides the loss of weight, which is equivalent to the amount of water displaced by the substance or its volume. Specific gravity can be determined using a chemical balance, but for accurate measurements, Steelyard balance or Joly's spring balance are used. For rapid determination of specific gravity, certain heavy liquids are used. Testing a mineral for a specific gravity value is a complicated procedure. For the layman, it is done by water displacement and requires a beaker and a scale. The weights of the beaker and the specimen are taken and noted down. The beaker is partially filled with water and the level of the water is noted. The mineral is put into the beaker with water and the water level rises. The difference in the amount of water before the specimen was put in and after it was put in is noted. The mineral is taken out and the water is spilled out. Then the beaker is filled with amount of water that the specimen displaced and measured. The difference in weight of the beaker when it was empty and the current measurement, that is the beaker with the displaced water, is the weight of the displaced water. The weight of the displaced water has the same volume as the specimen, but a different mass. The weight of the specimen is divided by the weight of the displaced water and the number attained is the specific gravity of that specimen. This test cannot be conducted for an embedded mineral, but only for a single crystal or mass for obvious reasons. A Steelyard balance or a Steelyard is a straight beam balance with arms of unequal length. It encompasses a counterweight which slides along the calibrated longer arm to counterbalance the load and indicates its weight. A Steelyard is also known as a Roman Steelyard or Roman balance. A Steelyard consists of a balance beam which is suspended from a pivot or fulcrum which is very close to one end of the beam. The two parts of the beam which flank the pivot are the arms. The arm from which the object to be weighed, that is the load, is hung is short and is located close to the pivot point. The other arm is longer, is graduated and incorporates a counterweight which can be moved along the arm until the two arms are balanced about the pivot, at which time the weight of the load is indicated by the position of the counterweight. The Steelyard exemplifies the law of lever, wherein when balanced, the weight of the object being weighed multiplied by the length of the short balance arm to which it is attached is equal to the weight of the counterweight multiplied by the distance of the counterweight from the pivot. According to Mark Scheifsky of Harvard University, the Steelyard was in use among Greek craftsmen of the 5th and 4th century BC, even before Archimedes demonstrated the law of lever theoretically. Roman and Chinese steelyards were independently invented around 200 BC. Steelyards dating from 100 to 400 BC have been unearthed in Great Britain. Steel yards and their components have also been excavated from shipwrecks of Byzantine period in the Mediterranean and in the Red Sea, such as the 7th century wreck at Yasiada, Turkey, and the mid-1st millennium shipwreck at Black Asarka Island, Eritrea. The Oxford English Dictionary suggests that the name steel yard is derived from the steel yard, the main trading base of the Hanseatic League in London in the 14th century. Steel yards of different sizes have been used to weigh loads ranging from ounces to tons. A small steel yard could be a foot or less in length and thus conveniently used as a portable device that merchants and traders could use to weigh small ounce sized items of merchandise. In other cases, a steel yard could be several feet long and used to weigh sacks of flour and other commodities. Even larger steel yards were 3 stories tall and used to weigh fully laden horse-drawn carts. A Scandinavian steel yard is a variant which consists of a bar with a fixed weight attached to one end and movable pivot point and an attachment point for the object to be weighed at the other end. Once the object to be weighed is attached to its end of the bar, the pivot point, which is frequently a loop at the end of a cord or chain, is moved until the bar is balanced. The bar can be calibrated so that the object's weight can be read off directly from the position of the pivot. This type is known as Sweden, Denmark and Norway type. Specific gravity of the substances is determined by using Joule spring balance. This instrument was invented by the German physicist Philipp von Joule in the year 1864. It consists of a spring fastened at the top to a movable arm. At the lower end, the spring is provided with 2 small pans, one suspended beneath the other. The lower pan is kept immersed to the same depth in water, while the other one hangs in the air. On the upright stand behind the spring is a mirror on which is engraved or painted a scale of equal parts. The specific gravity of an object, typically a solid, is determined by noting how much the spring lengthens spring when the object is resting in the upper pan in the air, and then when the object is moved to the lower pan and immersed in water, and they are recorded as W and W dash, and hence the specific gravity is determined as equal to W divided by W minus W dash. For rapid determination of specific gravity, in distinguishing yellow sapphire from citrine or blue sapphire from iolite, certain heavy liquids are helpful. Bromoform with a specific gravity of 2.89 is a readily available liquid for geologists. When stones are dropped into bromoform, sapphires specific gravity of 4 rapidly sink, while the other two, that is citrine or iolite with a specific gravity of 2.65 will float. Other commonly used liquids are methylene iodide, that is diiodomethane, which is having a specific gravity of 3.33, and chloric solution, that is thallium malonate and thallium formative in water, which is having a specific gravity of 4.15. Specific gravity of bromoform and methylene iodide can be reduced by adding toluene, which is having a specific gravity of 0.865, or acetone, which is having a specific gravity of 0.792. Water can dilute chloric solution. It is advisable not to mix two heavy liquids, as the mixture turns black. Heavy liquids are stored in amber colored bottles so that they get darkened. Most heavy liquids are corrosive and their fumes are harmful to the eyes. Chloric solution especially is extremely dangerous and poisonous. Although bromoform is commonly used as heavy liquid, it is hazardous to health. Alternatively, non-toxic sodium polytungstate, also known as sodium metatungstate, having a specific gravity of 2.820, dissolved in water is recommended, and the specific gravity of the liquid can be taken up to 3.10. A set of labeled bottles containing heavy liquids reduced to required specific gravity is handy in rapid determination. Standard indicators can be kept in liquids to check specific gravity. For example, quartz forms the indicator for a liquid having specific gravity 2.65, and for specific gravity 2.71 the indicator is Iceland spar. Specific gravity 3.52 indicator is diamond, and the specific gravity 4 indicator is corundum. Now, the sixth module of this talk is on the problem of specific gravity. How do we calculate the specific gravity of a mineral?
Depending upon the size of the mineral, we have different methods. The most common technique that one can use or even fabricate is for specific gravity determination of normal size specimens is the use of Walker-Steelyard balance. Irrespective of the method, the basic principle involved in the measurement of specific gravity is that specific gravity of a mineral is the ratio of the weight of the mineral to an equal volume of water. If weight of the mineral in air is Wa, its weight in water is Ww, then Wa minus Wb is the weight of displaced water by that mineral. The specific gravity therefore will be equal to Wa divided by Wa minus Wb. It generally consists of brass and consists of a long graduated beam. One end is pivoted and counterbalanced by a heavy weight from the short arm. The specimen tied with a thread is moved along the beam until it exactly counterbalances the heavy weight which is shown by the beam, being exactly horizontal and coinciding with the mark in the slot through which the beam passes. The reading, the weight of the specimen in air is designated as A. The specimen is then immersed in a beaker full of water, and the tied specimen is then moved along till it counterbalances it again, and the reading is designated as B. This represents the weight of the specimen in water. These two distance readings are inversely proportional to the specimen weight in air and water respectively. Specific gravity is given by the formula weight in the air divided by weight in the air minus weight in water. However, since the two distances are inversely proportional to the specimen's weight in air and water, the formula becomes specific gravity equals B upon B minus A. It should be remembered that the specific gravity of the crustal rocks lies between 2.65 and 2.75. It is significant that most common mineral, quartz, is also having a specific gravity of 2.65. A density around 2.65 to 2.75 can be termed as medium, those above 3 as high, and those below 2.65 as low. Silicates, carbonates will naturally have a density or specific gravity which will be between 2.65 and 3.5 as compared to metallic minerals, which will have an average specific gravity of 5. Native copper, for example, has a specific gravity of 8.8, whereas the king of metals, gold, is having one of the maximum specific gravity of 17.
For example, a mineral with a mass of 150 grams displaces 60 milliliters of water. The specific gravity is equal to mass of mineral divided by mass of water displaced by the mineral. What is the mass of mineral? Mass of mineral is 150 grams. What is the volume of water displaced? It is 60 ml. 1 ml of water has a mass of 1 gram. So, the mass of the displaced water is equal to 60 grams. Gravity is equal to 150 grams divided by 60 grams, that is equal to 2.5. Although the specific gravity test offers an important tool in identifying gemstone, 4 factors have to be borne in mind. What are they? They are: minerals are capable of possessing other elements in solid solution, and hence the specific gravity can deviate from the normal value to a certain extent. For example, depending upon the impurity, specific gravity of tourmaline can vary between 3 and 3.2. Specific gravity of intermediate members in a solid solution series depends on relative proportions of end members. For example, olivine. Number 3, there can be more than one mineral having the same specific gravity. Example, diamond specific gravity is 3.52, and spin and spinel, they have specific gravity 3.50 and 3.54 respectively. Presence of inclusions can alter the specific gravity. Thus, this test of specific gravity has to be supplemented by other confirmatory tests. Crystalline substances which possesses analogous chemical formulae and similar structural features, that is isostructural, are said to be isomorphous. Often a number of related minerals are isomorphous. Members of isomorphous series are not only isostructural but also have ions of similar sizes, valency, and occupy similar structural sites. Hence, there will be easy substitution of cations between two members of the isomorphous series. Isomorphic group is a group of minerals with the same atomic structure but different chemical composition. Atoms of different elements representing equivalents in minerals of this group have same crystalline nature. FeCO3, that is iron carbonate, that the mineral is siderite, and calcium carbonate, mineral is calcite. They belong to the same isomorphic group in the carbonate class, because in both the cases there are 6 oxygen around each iron and calcium respectively, 3 oxygen around each carbon, and 1 carbon and 2 iron or calcium around each oxygen. More commonly, the different minerals possessing the same atomic structure reflects similar chemical and physical properties and similar crystallography. Some examples of isomorphic or isostructural groups are: in the oxide class, hematite group, spinel group, rutile group are there. In the carbonate class, calcite group, aragonite group are there. Sulfate class, barite group minerals are there. In the silicate class and in nesosilicate subclass, garnet group minerals are there, and in Inosilcate-pyroxene subclass, sodium pyroxene group is there, and Inosilcate-amphibole subclass, sodium amphibole group is there. Isomorphism can exist with minerals which are not in the same mineral class. Since they are not in the same mineral class, they cannot be in the same isomorphic group. For example, NaNO3, that is nitratite, is isomorphic are isostructural with the minerals in the calcite group of the carbonate class, including siderite and calcite. This phenomena of polymorphism is to a certain extent opposite to isomorphism. A substance of the same chemical composition assumes different crystal structures depending upon the temperature and pressure conditions prevailing during its crystallization. This is what is known as polymorphism. Good example of polymorphism of carbon minerals are diamond and graphite. Their properties are absolutely different. Diamond, hardest of the minerals, graphite has hardness 1. Density of diamond is 3.5 and that of graphite is 2.2. Diamond crystallizes in a cubic system, graphite crystallizes in a hexagonal system. This is mainly due to the location of carbon atoms differently in graphite and diamond. Bonding of the atoms of carbon in graphite is less strong than in diamond. The bond length in graphite is weaker compared to diamond. This property has made diamond hard and graphite splittable. Polymorphic group is a mineral group belonging to the same mineral class, all having the same chemical formula, but different atomic structures. These usually form or are stable under different temperatures or pressures, whereby the same cation forms a different crystalline nature. With the same anion or the same crystalline nature exists, but there is a different bond angle between polyhedra. The difference in atomic structures result in polymorphs often forming in different crystal systems. Some examples of polymorphs are calcite and aragonite. Both are having the chemical composition CaCO3, but calcite is hexagonal and aragonite is orthorhombic. The next example is pyrite and marcasite. The chemical composition of both pyrite and marcasite is FeS2, that is iron sulfide, but pyrite forms at a high temperature and is isometric, while marcasite forms at a low temperature and is orthorhombic. The next example is the quartz, tridymite, cristobalite, stishovite and coesite. All are having the chemical composition of SiO2, that is silicon dioxide. Quartz forms at a low temperature and forms in the hexagonal system. Cristobalite forms at a high temperature and crystallizes in tetragonal system, while tridymite is an intermediate temperature quartz form which crystallizes in orthorhombic system. Coesite is stable at high pressures and is associated with meteor impact and is a monoclinic mineral, whereas stishovite is tetragonal and is thought to be associated with rocks from the Mars. The next example of the polymorphic forms are kyanite and andalusite. Kyanite and andalusite, they have the chemical composition Al2SiO5, that is silicate of aluminum. But kyanite is a triclinic mineral and is formed at a high temperature and pressure, and andalusite is orthorhombic and is formed at moderate temperature. The next example of this polymorphic mineral is microcline, orthocline, sanidine. All are having the chemical composition KAlSi3O8, that is potassium aluminum silicate. However, microcline is a triclinic mineral and is the low temperature variety, whereas sanidine is a monoclinic mineral, but it is a high temperature variety, and orthoclase is a monoclinic mineral which forms at an intermediate temperature. Kinds of metamorphism. Two types of metamorphism are recognized. Accordingly, number 1, reversible polymorph, where change from one polymorph to another takes place at a definite temperature and pressure, or number 2, irreversible polymorph and can change in only one direction at a certain temperature. The subclassification of this includes number 1, enantiotropy, a reversible change, as it can be seen from quartz to tridymite and tridymite to quartz, or graphite to diamond, diamond to graphite. Next one is monotropy. Monotropy, a one-way change between polymorphs, as we can see in marcasite to pyrite. Marcasite to pyrite, but not vice versa. That means it is irreversible. Also, polymorphs can also be categorized as to the nature of their change in respect to the degree of reconstitution of the atomic structure. Number 1, reconstructive change is the breaking of atomic bonds and a reassembly of structural units. This type of change involves a lot of energy and the change is not readily reversed and is sluggish. For example, quartz to tridymite, tridymite to cristobalite. Number 2, displacive change. Atomic bonds are not broken and the original structure is maintained. There is only a slight displacement of the atoms resulting in different bond angles. This change is instantaneous and involves little energy. Example, high temperature quartz to low temperature quartz. Third type is the order disordered change. Microcline, which is having the chemical composition of potassium aluminum silicate, that is KAlSi3O8, has an ordered arrangement of the silica and alumina in its structure, while the same for orthoclase is disordered. The disordered form will have more symmetry since it forms at a higher temperature. Number 4 is other groupings. Minerals grouped based on the same general or empirical formula, such as the pyroxene, amphibole and mica groups. The property of specific gravity is much useful in the identification of minerals. Certain minerals with identical other physical and optical properties can be distinguished with the help of the specific gravity. Minerals are capable of possessing other elements in solid solution, and hence the specific gravity can deviate from the normal value to a certain extent. Depending on the impurity and presence of inclusions in minerals, determination of specific gravity in such cases requires extra caution. However, this test has to be supplemented by the other confirmatory tests. Isomorphic minerals are isostructural in nature and also have ions of similar sizes, valency and occupy similar structural sites. Hence, there will be easy substitutions of cations between two members of the isomorphous series, depending upon the temperature and pressure conditions prevailing during its crystallization. Polymorphic minerals are formed. Thank you very much.